Computer, when is Pi Day?
Pi Day was today.
Hey Google, when is Pi Day?
Pi Day is on Thursday, March 14th.
Happy Pi Day, everybody. I'm a big math fan, and so this is a day that I would like to celebrate. Unfortunately, I did not really get to celebrate February 29th very much, which is significant to geeks and nerds, but here we are at Pi Day, and I'll take Pi Day. So I thought I would go around some things for pi and have some fun with math and circles for today. Various things. I don't know how long this video is going to be. Sorry if you don't find it interesting, but free speech, and so I find it interesting. So some fundamentals of pi. Pi is a unitless constant. It is, of course, defined as the ratio of a circle's circumference to its diameter. And it is an irrational number. It neither ends nor repeats. And it's been in use for a long while. So first of all, let's do some etymology. Circumference. Let's define some terms. Well, obviously we know that the circumference of a circle is the perimeter of it. But this one actually comes from Latin, and if you know some Latin roots of English words, maybe you saw this one coming. It comes from late Middle English, from Old French, which comes from Latin, so from the Latin word circum, meaning around or about, and faire, which means carry or bear, so to carry around. And circum, how about circus? Today, when we say the word circus, we think of an amusement, a temporary amusement park, the traveling amusement park, if you will, with animals and acrobatic acts and things like that. But that comes from the Latin word circus, which means circle. When you talk about the ringmaster of a circus, the ring in ringmaster refers to the large circle on the ground that separates the performers from the audience in a circus. How about that? And so that one comes from Latin. And diameter, you might have seen this one coming too if you know Greek roots. But it comes from dia, which means across in Greek, and metron, which means measure. So you're measuring across. So how about that? Etymology is very useful. You can use it to extrapolate your understanding of many different concepts and words. And mnemonically, that helps a lot in your understanding of mathematics and science and language and the natural world and people's relationship to each other between different languages and cultures and things like that. Here's a website I found on WikiHow, a webpage I found on WikiHow. Some methods of approximating pi. Of course, and there's a thing I want to say here is that no matter how elementary you want to consider your method to be, first of all, it should be fun. I hope it's fun. And number two, keep in mind that any value of pi that we have come up with is an approximation because it's a non-terminating, non-repeated decimal. A very obvious one, of course, is to simply get a physical circle. Measure the circumference, measure the diameter. With a piece of string here, it's illustrated, and then calculate circumference over diameter. You got to be accurate with that, of course. And the less error you have in your measurements and your materials, the less error you will have in your calculation. Method 2 here, calculating pi using an infinite series. This is the Gregory-Leibniz series. This is not the truest formula of it because you can't necessarily see the pattern. I suppose you can, but let me see where is it here? Here we are, the Gregory Leibniz series. This comes from crypto.stanford.edu. So at Stanford University. So here's the Gregory Leibniz series formula. And it starts with the Taylor series. I remember hearing about the Taylor series and the Taylor expansion, but I've forgotten what that means. And this is in my opinion, the easiest way of calculating pi. And we'll get into that one a little bit later. Here's another infinite series called the Nilakantha series, which I have never heard of before, but that's interesting. And here's a physical experiment one called the Buffin's needle. And this is sometimes they're illustrating with hot dogs here, but you can also do it with straight pins. And the idea is you take a straight pin and you put it across, and you draw lines parallel that are equal in separation to the length of the needle, and then you drop a whole bunch of identical needles of identical length, and you count how many times a needle crosses one of the lines, and from that you can approximate pi. This one, I didn't understand it. Maybe I still don't very much, but somebody pointed out that what you're doing is you're not using just straight lines. What you're doing is you're representing diameters with the pins, or in this case, hot dogs. Here's a method 4, which I think is silly. It says here, calculating pi using a limit. So you pick a large number, they picked that one, and then they use a calculator and put it into degrees mode instead of radians. And the reason I think this is silly is because you're using 180 degrees divided by x, your large number. And, 180 degrees by definition is pi, so you're trying to use a number to define itself. And that's why I don't like that one. Method 5, using arcsine function or inverse sine functions. And so let's go through this one quickly. Pick any number between -1 and 1. This is because the arcsine function is undefined, of course, outside of that. And then you've got this formula here. Well, okay. That's interesting, but it doesn't quite tell me where they got that formula from. Community Q&A. Okay, so that's the 5 methods that they illustrate here on WikiHow. Community Q&A, is 22/7 equal to pi? No, that's only an approximation. Pi is irrational and cannot be put into fractions. The Gregory Leibniz series here, this one is the one that I'm thinking of here. Wikipedia has a whole article here on just approximations of pi. Record approximations of pi by year. Wow. Number of decimal digits. Now this is interesting. Graph showing the historical evolution of the record precision of numerical approximations to pi measured in decimal places, depicted on a logarithmic scale. Time before 1400 is not shown to scale. On the x-axis they're referring to. And the record was just set in 2016, I believe it was, for a calculation of pi to 100 trillion digits. And that was a gigantic leap. And, I love these sort of infinite mathematical quests like this. As a matter of fact, Wikipedia itself, in the article on pi, mentions the quest for further digits, like prime numbers, the next prime number. We have now reached an accuracy within 0.4% of the true value. Oh. Reached. Okay, sorry. Reached an accuracy of within 0.4% of the true value before the Common Era. And it's not just the Greeks either. The Chinese, ancient Chinese people were able to approximate it too. and Indian people as well. So that's probably not something that I thought of before. I probably should have. The record, here's what's interesting here, to another point of discussion that I'll get into. The record of manual approximation of pi is held by William Shanks, who calculated 527 digits correctly in 1853, and he did that by hand. Because I don't think even mechanical computers were invented by then. Since the middle of the 20th century, the approximation of pi has been the task of electronic digital computers. For a comprehensive account, see Chronology of Computation of Pi. Yet another article from Wikipedia specializing in pi. Here we are. I'm sorry, not 2016, 2022, June 8th. The current record was established by Emma Haruka Iwao with Alexander Yee's Y Cruncher. That's for lack of a better term, a computer program that's run on Google Cloud with 100 trillion digits, 10 to the 14th power. Let's look at this graph here, the record approximations of pi. The y-axis is a logarithmic scale, and the x-axis up to 1400 AD is not to scale. But here we have, would be nice if it was, if the x-axis at least was scaled properly. So 10 to the 14th. Logarithmic resolutions are, rather than linear, are kind of hard for us to comprehend because it gets so big that we don't think logarithmically, naturally at least, I think, in my opinion. But that's fascinating. Let's go back to the original pi article here. And let's go back to, let's see, history. Here we are. Adoption of the symbol lowercase Greek pi. This is something I had never thought of before. I think what one of my college professors said was that it was short for the word proportion. But that, of course, assumes that you're speaking in English to begin with. And I'm not sure what the etymology of the word proportion is. Actually, that word proportion, the T-I-O-N at the end of it, implies that it's Latin. But here we are. So two guys, one of which I've heard of before, Leonhard Euler. Leonhard Euler popularized the use of the Greek letter pi in works he published in 1736 and 1748. The earliest known use of the Greek letter pi to represent the ratio of a circle's circumference to its diameter was by Welsh mathematician William Jones in 1706. So there you have it. In the earliest usages, the Greek letter pi was used to denote the semiperimeter, or semiperiferia in Latin, of a circle, and was combined in ratios with delta for diameter or semi-diameter, or rho for radius, to form circle constants. Before then, mathematicians sometimes used letters such as C or P instead. The first recorded use is Oughtred's delta point pi to express the ratio of periphery and diameter in the 1647 and later editions of Clavis Mathematicae. Oughtred, who is Oughtred? William Oughtred, also Oughtred, etc., was an English mathematician and Anglican clergyman. After John Napier invented logarithms and Edmund Gunter created the logarithmic scales upon which slide rules are based, Oughtred was the first to use two such sliding scales, etc. The earliest known use of the Greek letter pi alone to represent the ratio of a circumference of a circle's circumference to its diameter is by Welsh mathematician William Jones in his 1706 work Synopsis Palmariorum Synopsis Palmariorum matheseos. Synopsis: Palmariorum matheseos, or a new introduction to the mathematics. Oh, synopsis means introduction? Wait, or maybe, well, maybe that's not a translation from one language to another. Maybe he just gave it an alternate title. The Greek letter appears on page 243 in the phrase 1/2 periphery, pi, calculated for a circle with radius 1. However, Jones writes that his equations for pi are from the, quote, ready pen of the truly ingenious Mr. John Machen. I hope I pronounced that correctly, leading to speculation that Machen may have employed the Greek letter before Jones. Jones's notation was not immediately adopted by other mathematicians, with the fraction notation still being used as late as 1767. Leonard Euler, started using the single letter form beginning with his 1727 essay explaining the properties of air. Although he used pi equals 6.28, which is what we call 2 pi now, the ratio of periphery to radius, or circumference to radius, and in this and some later writing. Euler first used pi equals 3.14, etc. in his 1736 work Mechanica, and continued in his widely read 1748 work Introductio in Analysum Infinitorum. He wrote, quote, "For the sake of brevity, we will write this number as pi. Thus pi is equal to half the circumference of a circle of radius 1. So he's not even using, half the circumference of a circle of radius 1. So he's not even using that as the ratio, I don't think, is he? Well, it turns out to be the correct number. He's going about it in a roundabout way. That's definitely not the way I think of it, but anyway. Because Euler corresponded heavily with other mathematicians in Europe, the use of the Greek letter spread rapidly, and the practice was universally adopted thereafter in the Western world, though the definition still varied between 3.14, etc., and 6.28, etc., as late as 1761. So that's an important note to make, because many modern mathematicians and math fans, you can be a mathematician without having any credentials, I would say, have the stance that 6.28, etc., or 2 times pi equal to tau is a better number to use. So they define the Greek letter tau as having a value of equal to 2 pi, or rather circumference over radius rather than circumference over diameter. Modern quest for more digits. I love the word quest that they use here. Computer era and iterative algorithms.
Sorry, I'm not sure.
Yeah, I bet you aren't. So this goes through computer era, which I have not read through. Rapidly convergent series. Here's a fellow I have never heard of before. Srinivasa Ramanujan, working in isolation in India, produced many innovative series for computing pi. And that was 1914. New infinite series. Here we are. Rapidly convergent series. Modern pi calculators do not use iterative algorithms exclusively. New infinite series were discovered in the 1980s and 1990s. As recently as that, but are as fast as iterative algorithms, yet are simpler and less memory intensive. That is amazing. New methods were discovered in the 1980s and 1990s. The invention of computers was a huge, huge turning point in human history. Here are some equations. Monte Carlo methods. Buffin's needle, that's a Monte Carlo method. Monte Carlo method, my understanding of it is it relates to the city of Monte Carlo, which is famous for gambling, and of which I don't encourage, but of course gambling uses mathematical probability. And so anything in mathematics that's using a Monte Carlo method is simply using a brute force method of calculation. You run an experiment many, many, many times and use the numbers you get from that to approximate. Here's another one. Random dots are placed on a square and a circle inscribed. Random dots are placed on a square and a circle inscribed inside. And some formulas for that. Now here's another one that I had never heard of either. Another way to calculate pi is using probability. Using probability is to start with a random walk generated by a sequence of fair coin tosses. So heads or tails, or left or right, depending independent random variables, such that, yeah, oh, okay, they're deciding between -1 and +1 with equal probability. So the associated random walk is that summation. And they've got an example here, 5 random walks with 200 steps. The sample mean of the... Now this is amazing. Why would it come out of that? Why would pi just come out of randomization like that? There's a good, maybe not philosophical question, but a really philosophical hyphen mathematical question. I'll get to another one of those. Spigot algorithms, which I have not heard of before. Geometry, trigonometry, units of angle. There's our good friends sine and cosine. Eigenvalues. I remember I studied those, but unfortunately I don't remember what those are. And let's see, let's move a little bit on. Approximations of pi, we kind of covered that. Buffin's needle problem, we covered that. Oh, here we are. The solution for the sought probability P in the case where the needle length L is not greater than the width T of the strips. Oh, where the needle length L is not greater than the width of the strips, so it doesn't have to be equal? So L here does not have to equal T? Wow. Okay, that's a little bit more mind-blowing to me. Okay, so here we are, back to the Gregory Leibniz series. So we've got, they do it in, oh bother. They don't really show a good elegant equation here for it, but it's going off of this one. Pi is equal to 4 times this sequence. And you can see here that these fractions are getting smaller and they're alternating in signs. So what you're doing is you're essentially overcorrecting with each additional term here inside the parentheses. And so you've got to keep correcting infinitesimally small, but each one of them is an overcorrection. And that leads to this. So this video here, this is by the YouTube channel Stand Up Maths, and his name is Matt Parker, and I believe he's British. And for quite a few years now, he's done an annual Pi Day video, and this is his most momentous, well, both momentum, yeah, having momentum, and monumental video so far. What he did was he gathered 200 people in a room for 5 days at the City of London School. And for 5 days, they worked on calculating pi via the Gregory-Leibniz series. No calculators of any kind were allowed in the room. And I won't spoil it for you. They did really good. It's still the biggest hand calculation in a century of pi. It's still topped only, as far as I know, by William Shanks, and he took decades to do his. Let's go on to this one. Oh, no, not go on. What I think, though, so he's done this for 3 years now, for Pi Day, 2022, 2023, and 2024. He has done a group hand calculation, and it's gotten bigger and bigger in terms of the effort each time, both the number of people and the amount of square space, floor area that they're taking up to do it. And it is my prediction that in a few years of further orchestration of this, they're going to break a record. And that's going to be a fun day. Or week, or whatever it is. But they're doing an excellent job on that. Here's one from the YouTube channel 3 Blue 1 Brown. This is an astounding thing here. And he claims that he's got an explanation. I've watched this first video, which explains the puzzle and gives the situation, but it does not give the explanation. The next video gives the explanation. What this is here is he's built an ideal physics engine with a computer, and so he's got a 1 kilogram mass and a 100 kilogram mass. And we're going up in powers of 100. And you slide the 100 kilogram mass at the 1 kilogram mass against a wall, and then so that it hits a wall. Like that. And what they're doing is they're increasing the mass of the greater mass by powers of 100. And they're counting the number of collisions that happen between the two blocks until they never collide again. So there's a 1 million kilogram. That would be 100 to the third power, I believe. Here's 100 million, so that would be 100 to the fourth power. And what you can see here is that it's getting the number of collisions, not counting a decimal point, are approximating pi. And I don't know why. That comes in the next video here. In the next video, why do colliding blocks compute pi? But where 3 Blue 1 Brown got the idea for this was this paper here by G. Galperin at the Department of Mathematics and Computer Sciences at Eastern Illinois University in Charleston, Illinois. And this is a paper from December 9th, 2003. It's irrational but well-rounded. Found on a printed t-shirt. Oh, that's cute. I love that they put that fun caption at the front of a completely serious mathematical scientific paper. I bet even Mr. Spock would be amused at that. So this paper is, how many pages actually? 20 pages long. I've not read it, but this is quite a phenomenal discovery, in my opinion. And of course, pi is not rational, even though it's well-rounded. This one comes from, this illustration comes from mightywombat.com. And that's a really amazing thing, because why in the world would these sliding blocks, which have nothing to do with circles, why would that approximate pi? And, of course, you can't have, spheres, otherwise, or even circles, cylinders, that is, even cylinders, circles, or spheres, you could not have those in here because they would not slide, they would just roll. So 3 blue 1 brown says that the circle is involving momentum, I think it was, and I've not gotten into that yet. Okay, here's another one by Mark Rober. Mark Rober is a YouTuber, very, very popular on YouTube. And what he is popular for is making science fun. I highly encourage anybody to follow his channel. So, my favorite William Shakespeare play is called A Midsummer Night's Dream. And in that, the character of Puck says that he can run a girdle around the earth in, I believe he said it was 20 minutes, but time is irrelevant for this. So but the point here is running a girdle around the earth. And the problem here, or the riddle, if you will, is that if you run a girdle around the earth, and then you find out that instead of lying on the surface, it's supposed to be, say, 1 meter above the surface, then how much length of rope would you have to add? Say, for example, we're using feet or we're using meters. The unit that you're using does not matter, just that you're consistent with the unit that you're using. And so I'd like to go through a derivation of that after I show you this book. This is a book that I found that was recommended to me, Circumference and the First Round Table, a math adventure by Cindy Neuschwander and Wayne Guillen. And this is a fun and fictional mathematical adventure about the first round table. So you might want to share that with kids or even yourself. So let's do the girdle around the earth problem. Let's give a top-down view of the earth and the girdle. Okay, so we know that the circumference is equal to 2 pi times r. Okay, so that's if the rope is lying on the surface of the earth. If you find out that, so the circumference, we could call it meters, we could call it feet. Let's just say meters, because I like the metric system. So let's say that we instead need it to be 1 meter off of the ground instead. Well, then we're going to get a delta C that we have to add in somehow. So the delta C, the question is how much, if you wanted to be 1 meter off of the ground, the question is how much more rope would you need if it's around the earth? And so we're going to get a delta circumference, and that circumference is going to be equal to that delta C in the rope is going to be equal to two pi times r plus 1 unit, 1 meter, because that's what we're going to have here if it's going to be 1 meter above the surface. Okay, so that's the minus 2 pi r. That's going to be the delta in the circumference. So multiply that out, distribute it, you get 2 pi r plus 2 pi minus 2 pi r Well, that cancels that, and you get 2 pi units. So what that means is that equals approximately 6.28 meters. And the thing is, that's going to work regardless of whether you're using meters or feet or miles, and also regardless of what the radius is. So believe it or not, you're going to need 6.28 meters more rope, regardless of whether you put a rope around the earth and you want it to be 1 meter off the surface, or whether you put it around a golf ball and you want it to be 1 meter off the surface, or a basketball, or the circus, or the circle at the circus, or a CD, or your head. Anything. That's really interesting that it's independent of the radius. Another thing I wanted to point out is that the difference in, not the difference, we've got coordinate system, we've got a unit circle. Sphere is my favorite geometric shape. Oops, negative. Sphere is my favorite geometric shape, even though it more or less requires spherical coordinates to work with. But just in terms of its beauty, I guess. Maybe that comes from flat land, or rather sphere land. Which is a really good book. Sphereland is an unofficial sequel to Flatland. Sphereland was written in 1960. And it's a really, really good sequel. It's written by Dionys Berger. 2 pi radians. So radians and degrees. There's also gradients. Radians, degrees, gradients. But these are all the units of measuring angles. And mathematically, the one that's most elegant to work with is radians. Because as you go around the unit circle, at say an angle of theta, the length of the arc is going to be measured in radians. And if you go around the entire circumference, then the circumference of the unit circle is 2 pi radians. So it makes it very, very convenient to work with. And I cannot remember whether my calculus professors said that we just do that because it's convenient or because there's some sort of naturally occurring reason. Here's another thing I wanted to show. Integration. Let's see, volume of a sphere. Well, okay, so that's supposed to be dotted behind there. But if you have a sphere with a radius r, then you've got a certain volume and a certain surface area of that sphere, which can be expressed in r. And the surface area of a sphere, yeah. S-P-H-E-R-E equals 4 pi r squared, and the volume of S-P-H-E-R-E equals 4 thirds pi r cubed. Now, as I recall, these formulas were shown to me in 4th grade. That's when I was first introduced to them. And believe it or not, it wasn't I don't remember if I ever wondered where they came from, or why they were just presented to me without explanation of where they came from. But it wasn't until literally 10 years later, in either Calculus 2 or Calculus 3, that I was finally shown the derivation that proves that these are the equations for those values. And the reason is because you need calculus in order to do it. And I wonder if I had been shown that when I was in 4th grade, if I would have maybe not understood it, but at least have been interested in it to start learning more about it. Yeah. Sometimes we really underestimate children. And don't forget that we ourselves start out as children. And adults always underestimate us, right? When we're children. Here's another one. There's the calculation of the area of a circle. I have a circle, 2-dimensional, and we have a radius r. Then the area of the circle is going to be, well, we know it as pi r squared, but the question is, where does that come from, right? We've also got the circumference c, and the diameter d. Well, the idea here is that you, again, need calculus for this, to figure out where that formula comes from. Or maybe it was in 4th grade that I was told this, pi r squared for a circle. Maybe not the sphere. I'm honestly not sure at the moment. But anyway, if you're going to do this, what you want to do is you want to use calculus to do it. And here's how. So if you've got, think of the circle as like an onion. You're going to be slicing it up into infinitely many pieces and adding up all those pieces. And those pieces are going to run from the inside. Actually, you don't have to use calculus to do it. I just remembered another method. But those slices are going to go from the inside to the outside, and they're going to have a certain area, a certain infinitesimally small area, and they're going to be added up from the inside to the outside. And the way that it works is, you think about what the area is going to be. Well, think of it in a strip with an infinitely small width, almost infinitely small, and we call that dr, and that's going to be the width. And then the length of that, if you uncurl it, if you will, so take any of these given layers and uncurl it from a circle into a straight line, it's going to have a c circumference. Okay, so the area of any of those is going to be dA. D stands for difference in this case. I guess DC as well. Then the area of that is going to be dr times dc. Well, we know what c is. C is 2 pi r. So we can substitute that let's see, am I following my own logic here? Well, yes, I think I'm trying to go in 2 different directions at once. let's do it without pi. If you go from the center to the outside, you're going to start at the point in the center, and you're going to end up with one that's the actual circumference length at the perimeter. Okay? Well, the area of this one is going to be 0. The area of this one is going to be whatever. And so you take all these little slices and add them up and set them right next to each other. You end up with a triangle. Well, guess what? This is going to be r. It's not to proportion because it's actually going to be like that, I guess. But this is going to be r at the base, and this is going to be c. And you've got your origin there. And so the area is going to be 1/2 the area of a triangle, 1/2 the base times the height, 1/2 the base times the height, which is c. And so the area then is 1/2 r times 2 pi r. The half and the 2 cancel, and you get the area is equal to pi times r, which is r squared. There's a non-calculus way of doing it. So, by the way, if you were trying to use tau, you would have to use, how would that turn out in tau? Well, maybe I'll do that for Tau Day, which I guess would be June 28th, 6.28. Right. So, I think that's everything. So, thank you very much, and don't forget, math is fun.